Opher workshop. We are going to restart the work, continue the Opher workshop with the talk of Hugo Camacho, Cosmology from the DES Y3, baryon acoustic oscillations and the combination of clustering and weak lensing. Go ahead, Hugo, please.
Yes. Thank you very much. So first of all, it's a pleasure to be here. So thank you very much for having me here. And yeah, so I'll be talking a little bit about this morning about some recent results from the dark energy survey, in particular results from the first 3 years of observations, this DSY3 data. And so this is a little outline of that I have for this talk. Basically, I'll be briefly motivating this talk, talking about the information content on photometric galaxy surveys. Then I'll mostly concentrate on the BAO feature detection on the data from the first 3 years of the dark energy survey. And I'll try to end up quickly overviewing the main cosmological results of the combination of weak lensing and clustering, also from the same data that was released some months ago, actually. So first of all, let me begin just briefly commenting about galaxy redshift survey. So all of us know that this is now during the last decades, basically surveys has gained enormous importance for cosmology. They not only have been releasing information about history and expansion and history of expansion and history of growth of the universe from, for example, spectroscopic surveys like BOSS, eBOSS, and in general, DSS, but also are beginning to deliver increasingly important cosmological constraints for wide area photometry. I mean, from these photometric galaxy surveys, of which the DES is one particular example. Basically, this is just to mention the main difference between these two things. Spectroscopic surveys, well, both basically deliver catalogs or maps of angular positions and some estimates of redshifts of galaxies or luminous objects or some tracers of the matter distribution in the universe. So photometric surveys basically do this estimation using photometry. And spectroscopic surveys can take like spectra of point objects. No, so the DES is a wide field photometric galaxy survey. No? So its main 2 components are basically the first 2 ones here, the first 2 bullet points here, the people and the camera. So it's more than 400 collaborators around the world from more than 25 institutions and more than from different countries around the world. And the main in the suite of observational opportunity is basically opened by this 570 megapixel camera, the DCAM, or the dark energy camera, which is located at the Blanco telescope in Chile, which is a 4-meter telescope. And basically some numbers about the DES. So it is completed now. It ran between 2013 and 2019. A little bit more than 5 years, less than 6. The Y3 data that I've been talking about here is basically between 13 and 16, 2013 and 2016. And it's a wide field survey, roughly 5,000 square degrees. It covers 5 bands, mostly on the optical, but also on the near infrared. And it's basically for these DSY3 data, there are cataloged more than 100 million galaxies, and having information on shapes and positions. No, so yeah, so the real DES people. So this nice picture on the top is from Campinas, from the DS collaboration meeting in Campinas some years ago. And then the not so nice one on the bottom is from this virtual collaboration meeting, just because of the status that the world is right now. And so yeah, so this is just nice pictures. So so my talk it's mostly about this little overview here, which is these like 4 steps to extract information content from this photometric galaxy surveys. And I want you to pay attention to this thing, because I will come back to this over and over. Basically, there are four things for main information content from this photometric galaxy surveys. So the first thing is, well, they deliver these catalogs that we were discussing a little bit about. And then from that, what people commonly do is construct some or measure some summary statistics, which will give you some data vector that you will use to use some kind of Bayesian inference to extract some cosmological interpretation and some cosmological relevance information. So in the second step, you at the same time that you can use these summary statistics that are like correlation functions or power spectra, you can also extract robust features, like for example the BAO feature. And so yeah, so the first thing that I will be talking about is this BAO feature. So basically what we know is that this is an imprint of the characteristical angular scale from CMB photons in the dark matter distribution that we observe today. And in particular, what we observe is basically a preferred angular separation between observed galaxies, which is basically the co-moving distance, which is the same one imprinted by the time of the coupling, or roughly at the time of the coupling by the sound horizon, which is this basically this integral from the inflation up to the epoch of recombination. And what you observe is this same angular scale on co-moving a distance on the sky, on the galaxy matter distribution. So we've been working here since the first year, since the data from the first year of DS on extracting this BAO information from DS data. And basically what I'm talking here is the extension of this DS-Y1 data, which is contained basically on this set of 6 papers from roughly 2018. And what I'm showing you here is the extension of that to DS-Y3 data. So first of all, how can we detect the BAO feature? So basically we need like 4 basic ingredients: some appropriate template for the clustering of matter, which is basically for this DS-Y3, it's something that was modeled with redshift space distortions, and it's isolating the BAO wiggles and this subtraction here of the linear in a non-wiggle power spectrum. It's applying some correction due to non-linearities, also with this damping, Gaussian damping here. And basically this thing, it's also has also a model which is associated Fourier transform. We basically project this into 2 summary statistics: the angular correlation function in the angular power spectrum, W theta and CLs. And we basically measure the bridge between relative measurements of the BAO angular separation on a determined fiducial cosmological model and on the desired actual measurement that we are doing. No? In order to extract that, you should also account from non-BAO features on these templates, which are basically modeled by nuisance parameters here, which are basically broadband terms that control the overall shape of your summary statistics, power spectra or angular correlation function. So here is just a little detail about the BAO template that we used. On Y1, we basically feed this nonlinear parameter, this Gaussian damping. On Y3, we are not doing this. We are basically computing this from first principles using this infrared resumation of long modes, which is basically based on works from Ivanov et al. And from recent years, based on this effective field theory of large scale structures. So on Y1, basically it's to say that in Y1 we were fitting together this parameter. On Y3 we basically modeled this thing, and this thing it's basically giving us a better, a lower bias on the estimation of the BAO, and roughly basically the same uncertainties. So It is good because you don't rely on this free parameter, and you can have different cosmologies for your template, because these things should be cosmology dependent. So that's the first reason why we do that. So for the analysis, we also benchmark with two different sets of mocks. One were log normal realizations being based on the Flask code. And the other one is basically a fast n-body COLA simulations based on Haley occupation distributions. No? So basically, we have two sets of independent mocks that are trying to mimic the basic properties of the BAO sample used from the DES data. And from those, we basically validate a covariance matrix, and we also validate the whole pipeline that we were using. So how we validate these things? So basically, we did a bunch of things. So the first thing is we changed, for example, we found what are the scenario for the broadband terms, and from different model analysis choices, like, for example, different binning for the angular correlation function here, and different covariance matrices, trying to find what are the better analysis choices that gives you less biases for the recovered BAO on the mocks, and the better statistics on the uncertainties. And the same thing was done for the angular power spectrum. So we found some sweet spot there for the set of analysis choices. And the thing that we proceed was actually to combine these two things, the angular correlation function and the angular power spectra. This thing was done using two different methods. First, we use this geometric mean of the likelihoods, which is this combination here on the right. And the other thing is basically accounting for the correlation between these two sets, which is shown in these figures here. It's basically a correlation between the alphas from both and the correlation between the uncertainties from both. And this thing is basically assuming Gaussian correlation between both. And what we found is basically these two methods gives you basically the same kind of result, the same kind of bias on the mocks and the same kind of uncertainties. But the combination of the mean of the two likelihoods basically gives better statistics on the uncertainty. So we fixed that as our fiduciary. So one thing pretty important that we did was basically blinding this data. While doing this full analysis, we did blinded when we applied to the data. Basically, in order to blind, we apply random offsets on this alpha parameter for the BAO. And besides of considering on the analysis actual alpha values, we only consider variations of alpha when you basically change different pieces of the analysis. And we establish in this analysis a precise protocol for this kind of unblinding tests. We basically check if the BAO were detectable, if it was robust, and if it has a good recovered error robust, and if it was a good BAO fit, basically based on the goodness of fit, no? And so in order to more or less, I will just say a few words about the second one, which is the robustness. Basically, how robust is this analysis when you change different pieces of the analysis choices? The first thing is, for example, we change we analyze what happens when you do not take into account, for example, here, just for showing an example, the clustering systematics. Basically, when you do not take into account the corrections for the observational systematics on your measurements. BAO is highly insensitive to that because it basically corrects the amplitude of the clustering, not the position of the BAO. And what we did was basically using the full distribution of the BAO recovered on a set of the full mocks, and compare that with the data. No? Here it's basically delta alphas. No? What happens when you consider the decontaminated fit with the contaminated fit by the systematics. No? And so here it's basically the question that we ask is if where the data falls in the distribution of the mocks. Basically, we put the thresholds here like p-values if you want. basically to say that we can fail at 90, 95, 97, or 99%, this kind of test. For this particular thing, none of these thresholds is going to fail, but for some others that we test, it happens. No? So for example, for the APS, there were different things that we changed, like for example, taking out one of the beams at the time on the tomographic analysis. These tomographic analyses were done with 5 tomographic beams, and when you remove one, different things can happen. So these are these first rows here. And also when you change, for example, the templates, and when you change the photometrics, the photometric redshift estimations that you are using, etc., etc. And so we found the analysis robust because we found that for all of these battery of tests, only one begins to fail at 90% threshold. And the probability for this to happen is like more than 40%. We will be in trouble if, for example, we were failing more than 6 tests at 90% probability, something like that. But this careful thing, it's basically in order to do not introduce selection bias from the observer or from the analysis. And only when we pass this battery of tests, we look at the actual measurements, which are this one presented here. So basically, these results are on the left, the angular power spectrum that we've measured on these 5 tomographic beams, and on the right, the angular correlation function. And as you can see here, we are basically isolating like the BAO feature, and you can see that these things have some signal to noise to obtain that. So at the end, what our measurements give us was a 2.7% detection at 0.8, which is like a 4% increased improvement with respect to Y1. And this thing represents the most precise BAO distance measurement in imaging data up to date, which is basically condensated here on this figure on the bottom, which is showing basically the up to date different surveys that have been measuring BAO, basically EBOS, DR16 compared to the DES Y3 data. And as you can see, the error bars that we have are comparable to these ones, but we only have one single point. So spectroscopic surveys can still be doing better than photometric surveys here. So the next thing that I will super briefly comment, because I have super few minutes now, it's basically to compare these with the results from the combination of clustering and weak lensing from DES. So I think I will mostly skip this thing, just showing you what people probably already know, that from DES people measure clustering, galaxy clustering on 2 different samples. These are angular correlation functions. Also measure cosmic shear, which is basically a correlation between galaxy shapes. And people also measure galaxy lensing, and combine these 3 things in order to do some cosmological analysis. And this cosmological analysis basically can be resumed on these constraints that we are presenting here. So the first thing is that the 3 parts of these data vectors, basically cosmic shear, galaxy lensing, and clustering, they are all consistent between them in principle and can be combined. But there's as people probably know, and we can probably discuss better during the discussion, there's one decorrelation between basically the angular correlation functions and the galaxy lensing measurements on the DES. This decorrelation can be measured on this phenomenological parameter X-lens, which is basically decorrelating the amplitude of these 2 things, which is controlled by the galaxy biases and basically the matter correlation function here. No? If these 2 things were correlated as it is expected as from the same kind of data, this phenomenological parameter should be consistent with 1. But actually what people found is something which is not consistent with 1 on one of the proposed samples for the DES. And this is still under investigation inside the DES. No? But more than that, what I wanted to show you is what happens when you basically combine DES weak lensing and clustering analysis, which is also called as this 3x2 point analysis, with information from this analysis that I just talked to you about of the BAO from DS. So here, these contours are basically in red, in black, the standard DS Y3 3x2 analysis, plus the DS supernovae. We should keep that in mind. And in magenta or in violet, you have the same data combined with the information from BAO. And so basically, these measurements that I just told you about BAO, what they are doing is they are having an improvement, at least on the Hubble parameter, only coming from DS of the order of 20%. This is pretty interesting because this is as far as we know, this is the first time that using only photometric data from the same experiment, we are looking at these kind of things. No,
Hugo, you have 5 minutes to conclude your talk.
Yeah. I'm basically finishing now. I actually kind of thought that I had less time. And so this last figure that I'm just showing you, it's basically the same kind of thing, but in the plane of omega matter and the Hubble parameter. And now comparing with Planck 2018, no, which is basically the best kind of constraints that we can have here. And the main thing is again, well, these pure photometric BAO detection inside the DS can actually improve what DS present as its main results, which is this 3x2 cosmology. You know? And the improvement, it can be measured at least on these two key parameters, the content of matter, omega matter, and the Hubble parameter H0. And in both is more or less of the same order, is more or less of 20%. So I just wanted to highlight the references for this. So there's a bunch of papers supporting this 3x2 analysis from DS. It's a total of 30 papers for that. And just for the DS BAO analysis that I just talked to you about, there's like 3 papers supporting this analysis. One is for the galaxy sample. One is for the galaxy mocks that we used, and the other is basically the one showing the main results that I tried to summarize here. So I'm just ending here with some summary and conclusions. Just basically, I just wanted to highlight that there's a bunch of novel methods that people have been developing to analyze these DSY3 data. And I wanted to highlight one of the things that we did for the BAO analysis, which is basically this a highly, how to say it, this, well, basically the blinding strategy for a BAO analysis on photometric surveys. This is the first time that, as far as we know, we are presenting this kind of detailed strategy. And what people, so in future years, we expect highly, well, better photometric data coming, for example, from the Reuven Observatory, the LSST. And we expect that this kind of analysis pave the way for these analyses that are to come. And basically, this 2.7 detection of the BAO feature with this DS data, I again highlight that this is like the most precise measurement done with imaging data up to date, and is, well, it's competitive on the redshifts, on the specific redshifts that it is with respect to spectroscopic analysis now. The other thing is, as I say, there are some tasks in particular for the DS, which is basically this puzzling apparent decorrelation between clustering and lensing amplitudes from DS. People here, our group is actually trying to tackle this from another point of view. This 3x2 analysis that I just presented was based only on correlation functions in configuration space. And as you saw, we work for the BAO also on Fourier space with the angular power spectrum. We've been working recently also on having, on preparing some analog harmonic analysis for this 3x2 analysis for the DES. And we hope that this brings some light into this kind of puzzling thing that the DES just published. And so the main thing, the bottom line of this, or the thing that I would like that you take home from this talk is basically that the combination of only photometric data from this DES Y3 analysis, it's basically telling us that even only putting one single point for the BAO analysis, this can be of great help for some particular parameters constrained on only using photometric data. I mean, to see the self-consistent of the DES and also to improve the constraints coming from only photometric data. This can be pretty useful for futures to come, for years to come. And that's more or less what I want to say.
Thank you, Hugo. You can use the reaction and raise your hand in the menu. You could click in directions and raise your hand. For questions. Any questions? Or you can write in the chat. We have time. No questions? Okay, thank you, Hugo, again. And can you leave the, yes, okay. Now we are going to hear Felipe Andrade-Oliveira. Felipe, can you?
Hello. Hello, can you hear me?
Yes.
Great, great. So
let me share your screen. Yeah. Compartilhar.
Sorry.
Host disabled. Yes.
Yeah, excuse me. What, Rogério?
Yeah, I have to make a Felipe co-host. I forgot. Sorry about that.
Ah, okay. Okay.
Just 1 second, Felipe.
No problem. No problem.
Yes, you can do it now, Felipe.
Okay.
Thanks for that.
Just a second. Here.
Good. Yes, we can see it.
So, hello everyone. I'm Felipe Andrade-Oliveira. I'm a postdoc here at the University of Michigan in Ann Arbor. But I've been a postdoc in Brazil for a long time with Nicolás and Rogério. So thank you very much for the invitation to talk today. It's a great pleasure. It's also a great pleasure to see some of my old friends here in the audience. So thank you all. And of course, to talk in the memory of the Professor Opher, that was my co-advisor during the master. So thank you. And today I want to talk a little bit about the dark energy spectroscopic instrument. It will be a very high level talk, but I hope you get some interest in this project that I think it's fantastic. So here, okay. So the idea of the dark energy spectroscopic instrument is a very ambitious idea that's create the most detailed cosmic map in the history. But this idea is not coming out of the blue. The people here in DESE has been working for decades with the former spectroscopic surveys like the Sloan, for instance, the BOSS, all the Sloan series. So here in this figure, I'm showing a beautiful figure that our colleague Claire Lehman did about our footprint. In this map here, we can see the parts of the sky that DESE is about to observe. And basically, DESE has two features for people that are not very working in this exactly subject. DESE is an instrument for do spectroscopy using fibers, optic fibers. And by DESE, we also mean that it's the Great Survey. So this instrument was installed in the Mayo telescope in Arizona. It's a 4 meters telescope. And this telescope have some adaptations in order to accommodate the instrument. And the idea is using the better part of observational time of this telescope and with this instrument to create a great survey to collect the data of literally millions of galaxies and quasars. This data going to very high redshift, up to 3.5, and covering 1/3 of the sky, the full sky area. So in the big picture, this is the first stage 4 experiment in activity, and it has just started. And even though we are already having some very thrilling results. So the spectroscopic survey is covering 14,000 degrees square. For a comparison with Sloan, the first and second generation had a box of 2 gigaparsec. BOSS raised for 6, and DESE is raising this box of the universe to 50 gigaparsecs. So we will have different objects observed by different redshift, of course, because it's easier to observe large red galaxies from lower the redshift, but to observe a redshift up to 3 or up to after 2, we need very bright objects like quasars, and the strategy here is slightly different. And in the middle of the way, we have the emission line galaxies. So finally, we have a very close survey of the bright galaxies, and this is to have a better use of the time of the telescope. So these galaxies can be observed in the nights where the conditions are not so good. So just to make a comparison, this is our universe in a box. So you can imagine that we have a box with the array and deck. That is exactly the flat sky that we are looking. And the depth being the redshift. So Vera Rubin Observatory with the LSST will have a huge number of objects, but these objects, since it's a photometric survey, you don't have a very detailed information about the redshift of them. On the other hand, DESE will have less objects, of course, but we have a fantastic resolution of 4,000. Just for comparison, I guess BOSS was up to 2,000 or 3,000. And we'll have this fantastic depth where we can probe the matter and the distribution of the galaxies all over this large redshift of 3.5. Of course, the motivation of the DES is the science, and we have three big questions that I guess all of you are very aware. And the questions are, is the late universe and the early universe explained by the same model? So is it lambda CDM a good model both for the past, both for the CMB, and a good model to explain the galaxy formation? And regarding the galaxy formation, other question is the growth of structure and the model for the expansion, the accelerating expansion, agree to each other? And finally, maybe this $1 billion or $1 trillion question is, what is the dark energy? So from the point of view of our community of cosmologists, is the dark energy lambda, or it has some more specific equation of state? Is it a constant fluid, or does it have some different behavior? So I'm talking now a little bit about the main probes, the main observations that DES is planning to do. So the first one is, of course, the cosmic expansion. The cosmic expansion represented by our Hubble parameter. In this case, DES will be a very robust estimating of this distance up to this redshift of 3.5 by using standard rules. And I will talk a little bit about these standard rules, but I guess Hugo probably said everything you need to know. And a very important question regarding this expansion is the tension between the data from CMB and the data from supernova. DESI will surely take part on this discussion, maybe on the side of CMB, maybe on the side of supernova, or maybe in the middle of the way. We don't know, but it will be very exciting. Again, the dark energy is the most abundant fluid in the universe, but we don't have a clear answer to what is accelerating the universe. The DES data will be able to place very tight constraints on the equation of state of the dark energy, or the lambda. So here in this plot, we have something for this parameter here that's different from 0 and this different from -1. It indicates that our model of our standard model may be something more complex than we are thinking it is now. Other very important question is about the modified gravity. The main theory of gravity, as you all know, is the general relativity. And any viable model of modified gravity can mimic the dark energy models, or mostly the lambda CDM behavior in the background. But for the growth of structure, they must be different, even more in large scales. So one of the probes that is quite sensitive is to the growth rate of the matter, and it will give us some very important answers about possible models of gravity that deviates from the general relativity. Another important question is about the neutrinos. DESI is quite sensitive to the neutrino mass. So today we have some constraints that goes to 0.06 electron volts for the sum of neutrino mass, and DESI plus the Planck data, and posteriorly the other CMB of stage 4 project together with DESI will be able to not only put some constraints on the neutrino mass, but maybe also about the neutrino hierarchy. The data from DESI is very sensitive to the clustering in dense regions, and this make a fantastic way of probe the non-Gaussianity. So this plot here is from the DESI document, and it shows the constraints from the WMAP, and that this tiny region here will be the constraints when we combine DESI plus the data from Planck from temperature and polarization altogether. So DESI is basically mostly doing two kind of measurements in from the cosmology point of view. So the first one is the acoustic oscillation that Hugo explained very, very well. So this is related to the sound horizon at the recombination, and it makes some imprints in the CMB. And also, when you observe a large number of galaxies with a high precision, you can see an excess of probability at some given scales. And this scales is related to this overdensity from the past when you had the photon baryon fluids. This will be extremely sensitive to this. It's actually projected to measure this quantity quite well, and also with the advantage of be able of measuring this in the transversal direction and also in the line of sight. The other important probe for cosmology is the redshift space distortion. So the galaxy maps are distorted since our radial coordinate is inferred from the redshift, and the redshift is distorted by the peculiar velocity. On the other hand, the peculiar velocity is directly related to the overdensity or underdensity. So in the linear case, this relationship between this distortion and the density or the potential is very simple. It's very linear for large scales, and we can have very insightful data from this kind of probe. So for this ambitious project, we need a lot of technology involved. So I want to give you a glimpse of the instruments. I will not talk about everything, of course, but I want to focus on some specific parts. So as I said in the beginning, DESI was installed in the Mayo telescope in the Kitt Peak, and the Mayo telescope is not a dedicated telescope constructed by DESI, but it's reused for this important project. And for using the Mayo telescope with the dark energy spectroscopic instrument, we had to build a corrector. We had to build a focal plane and a system of the fibers that will collect the spectrum of galaxies and quasars, and also, of course, the spectrographs. So the focal plane, it's a very interesting piece of object because the focal plane hosts the positioners. There's a lot of details in the construction of these because the precision for the focal plane should be astonishingly high, and we need to build some corrector of the path of the light in the way for this focal plane. And also focal plane is an important object because for people that know Sloan, it has a similar function as the plates in the Sloan survey. So in the focal plane are placed 5,000 positioners. These positioners are robots, and these robots are fixed, and they move from time to time in order to collect the different redshift information from the galaxy fields. So here is a very quick move showing the movement of these tiny robots. It's really hard to control these because they have some tiny fibers here, and the fibers has more or less the width of a hair, and the error in the positioner is about 10 microns. Just to make just to give you some idea of this, how precise it should be, the error is more or less the half of the size of a cell, of an animal cell. So beside this, we had of course, the spectrographers, we have the fiber systems, we have a very important software and a data control that's called ICS. Now it changed the name, but it's the control system. And I focused in the focal plane because I'm working in the focal plane, and it's quite interesting. So let me move to the next slide. So just to give some idea of our earlier achievements, the operation started properly with the data on May of this year. The operation was halted for 1 month for fixing the instruments. And even though DESI has broken the record of mapping three-dimensional location of 1,000 distant galaxies and quasar in a single 100,000 in a single night of October. And more interesting, in this month of November, it was collected 2.5 million of redshift. This number is equal to the whole number collected by the EBOS just in a single month. Of course, this is great because people with the know-how from EBOS, from Sloan, 60F, and a lot of different surveys are now dedicated to it. And we received from the Department of Energy, that's our main sponsor here in the United States, the award of the Project Management Excellence Award. This figure is from Michael Levy, the director of DESI.
Felipe, you have 5 minutes to conclude your talk.
Okay, I will cut this part talking about LINEA. Okay, I'm just kidding, Nicolas, sorry. But it's quite important to say that here in Brazil, we have been involved with the DES and these big surveys. This way before I joined LINEA, and we have the involvement with Sloan, and thanks to in-kind contribution that was proposed by Luis Nicolas and Rogério and others, we got some important positions in this fantastic project. So I had the pleasure of working in the Quick Look framework that's work for the data set. So this was just when I arrived in LINEA, and it was a quite important part of my career to learn how to deal with this state-of-art projects. And just a quick advertisement. LINEA is open to some PI positions. So I do advise people interested to apply, because it's the state of art in cosmology. And now we have 2 PIs. Flavia Sobreira is one of them. She works in large-scale structures and neutrinos. And Rogério Riffel from URGS studied the stellar population and the physics and chemistry of emission line gas of activity galaxy nuclei. So just to finish it, my final remarks is that DESI has just started. It's about to become the largest spectroscopic survey in the history. For sure, it will give a very insightful understanding about our fundamental questions in cosmology, about dark energy, the nature of the dark energy, about what's the best gravity model if we find some deviations in large scale from the general relativity, about neutrino mass, and a lot of different things that is going way beyond the cosmology. So cosmological papers is going to start in 2023 when we have the first year of the sample complete. And it's quite exciting because it's not only science, it's about the technology, it's about the relation with the people, and about of doing mistakes and learning from mistakes. And by mistakes, I mean from the collaboration and strategies for the next generation of experiments. So again, thank you very much. Thank you, Luis. Thank you, Rogério. It's a pleasure to be here, and thanks to our sponsor. And of course, thank you in the audience. That's all.
Thank you, Hugo. You complete in less than 24 minutes. It was an impressive instrument, that one that you talk about. Any questions? You can use the reaction at menu and raise your hand. Or write in the chat.
Odilio,
Yes?
it's good to remind people that we have also the opportunity of asking questions at the end in the paredão.
Yes, yes. There will be a discussion section starting at 3 o'clock this afternoon for all the speakers talking during the day. This is also an opportunity. But any questions now for Felipe? Okay, then we will have a break and return at 11:30. Okay.